Okay, I'm going to get started. So the way today's review session is structured is I have a bunch of stuff to go over on the .cam, and that'll be the majority of what I'm doing. I like to just go over key concepts or concepts that I notice are often most difficult for students to understand in the way that I'm going to be testing on the exam. And during the entire session, Jacqueline is in the back of the room. So if at any point you have a specific question about something that's being talked about the practice test or anything, you're welcome to go back there and talk with her. Then she'll also come up and help because I have a couple practice exercises that we're going to go through towards the end part of the session. Mostly on practicing vectorizing, condensing code, and that's about it. So that's what we're going to be doing. I am recording this. I don't know. Hopefully it doesn't get messed up. So let's get started. So the first thing I like to start with is the dot operator. So we've obviously talked a lot about this throughout the semester. It comes up constantly. It's something that we always play around with when we're writing the code and something isn't working. But what's different about the final exam is that I'm going to be asking you questions, either specific or through solving a problem, that requires you to understand why and what and how, not just putting the dot there to fix it, you know, or memorizing that the dot needs to be there in certain situations. So I'm really looking for you to understand the difference between having the dot and not having the dot. So just as a reminder, for operations of powers, multiplication, and division, there's the option of having the operator with and without a dot. So I think we all know that the dot means element by element, and without the dot it means some sort of matrix algebra or something else. So let me just give a couple examples and we can just go through what is actually happening with these two options. And again, this is one of the main reasons that I added linear algebra to this class, because it kind of forces you to have to think about the difference between these two. So I'm going to create a couple 1D arrays, a 2D array, and then a scalar, and save them all to variables A, B, C, and D. Okay, so if you're ever doing scalar to scalar or scalar to vector operations, those are all the cases where the dot is not necessary. So when you're writing code using anything, so like if you were doing 2 times d, so 2 is a scalar and d is a scalar, there's no need to have the dot there. Now if you put the dot there, it does the same thing, but by putting the dot there, it makes it seem in a testing environment that you don't actually understand what the dot is, if that makes sense. So there's going to be, I'm going to test you on that understanding in that way at some point. The same thing goes with the scalar to vector operations, which would be like d times a. Again, if you put the dot there, it would give you the same result. There would be no difference, but it's not necessary and it's not needed, so it shouldn't really be there, if that makes sense. So if you're, I explained this in lecture a little bit, if you're writing out like an algorithm on one of the last two problems, and you use a dot when it's not needed, that's not where I'm going to be like taking points off. I'm not going to be picky about stuff like that. But if the question itself is on your understanding of the dot operator, that's where I'm going to be expecting you to understand this difference. Does that make sense to everyone? Okay, so the only case where you have to be careful about the difference is when you're using vector to vector operations, which we do quite a bit because we've been trying to understand how to vectorize code because that's really how MATLAB is set up. So in that case, if you did A times B, that's not the same as A dot times B. And we run into these types of problems constantly. And what I'm really looking for you to be able to do is to be able to show me that you can understand and write code that does either of these two things, either through their application or through reading and writing simple code, like on the first couple of problems. So for example, if you're doing A dot times B, that's element by element multiplication. So it's going to take the A matrix, the A array, and multiply it by the B array. And all it's going to do is take the first element of each array and multiply them by each other and put it in the same position in a new array. And then the second elements will be multiplied by each other, etc. And it will leave you with whatever the element by element multiplication gives. Versus if you're going to do the multiplication symbol with vectors without a dot, it's doing matrix multiplication, and the only time we really used that for most people is in linear algebra. So if you take the C2D array, and again, this is varying difficulty for different people because people have very different backgrounds in linear algebra. Some people had it in high school, some people are taking linear or differential equations right now, and I've seen it through that. But all it does is it just follows matrix algebra rules, and so it's going to take the first row and multiply it by the first column, and it will go in the first position. So it's going to be 1 times 1 plus 2 times 3 plus 3 times 5. And since there's no other columns in the second array, there's no other columns in the final matrix. And so then you're going to move on to the second row times the first column. And then finally, the last row by that first column.
So that's C star A, and is that just like
a transpose, because I just drew the array as a row vector. So for the dimensions to agree, so the dimensions with matrix algebra have to have the inner dimensions agree. So the three.
So if you didn't have the total transpose, whatever you call it, it would work.
That's right. Yeah, I could have just drawn A that way, but I wanted to use the same one. So okay. And then once that algebra gets worked out, you get a 3x1 result from that. And this is, very much the same sort of dimensionality that comes out of the linear algebra problems. Okay, so that's the first thing, is the dot product. And again, remember that one of the things that you have to start thinking about when you're doing summative assessment like final exams is that we're not just going to be asking you to have knowledge on some of the stuff that you were being tested on in quizzes and labs, but to have like a full understanding of it. So it's not just get it to work and put the dot there, but make sure that you think about and understand what that dot's doing. You have a question?
So this is a vector by vector operation, so wouldn't there have to be a
So these are two options. This would be option 1. This would be an option where it's element by element multiplication, where you're taking each element of the two arrays and multiplying them by each other. And this would be the second way to do vector by vector operations, and that's using matrix algebra. And that does not have a dot. Any other questions? Okay, the next concept that I'm going to go over is strings. Again, I feel like this is something that really tells me a lot about your understanding of arrays, functions, and strings. But unfortunately, what a lot of people do is memorize the syntax rather than understand it. So I'm just going to explain the syntax of how to use functions with arrays. And there are things that we've done many, many times starting from the very beginning of the semester. But it's actually really a lot easier now looking back at that time because you guys understand a lot of things a lot better than you did when you were first using some of these things. So for example, we used the disp function a lot in the first part of the semester, or fprintf. I'm going to leave fprintf out of this because the syntax is very different from anything else that these other functions use, but fprintf is, I feel like, a little bit more straightforward. It's just memorizing the syntax of it, where this is all about arrays. So if you want to display a string with nothing else, you can just put it into the disp function and it will display the word hi, for example. Another similar function that does this is like the title, xlabel, ylabel functions, which work the same as disp, which is why I focus so much on disp. And there you can just give it a string and that's what will be placed inside the title. However, most of the time you want to do something a little bit more customized than just being able to display a hard-coded string into some of these statements. So for example, sometimes you want to incorporate two different strings and maybe one of the strings is saved to a variable. We've done this through saving them through input prompts, reading them in from files, various things. But let's just say you have a variable that might have a changing string in it that you want to incorporate into a disp statement or into a title statement. So the next level of these functions is that if you want to include more than one string, you need to put those strings into an array. So again, you use the parentheses, which tell it what's going into the function, but then you have to put all of your strings into an array with square brackets. So for example, I can start off my string with the word hi, and then I can concatenate on another string saved in the variable m, and that variable m can have a string that changes, so that way every time you run your code, the disp function will update with whatever is held in that variable. So all we added here is square brackets to group our strings together in an array because that's required by the disp function. It either needs one string or one array of strings. And the title function works exactly the same as that. It's the exact same syntax. It also can only receive, I don't think that I wanted to write hi, but I'm just going to write the same thing. It also can either only receive a string or an array of strings. And all I'm doing here is I have one string that's in the single parentheses, or I forgot the comma here, and then a second string which saved in a variable. I think it works with commas or spaces just like regular arrays do, but commas make it easier to tell. So here we have one string, here we have combining more than one string, and then the last thing that we did often is incorporate a numeric value that's saved to a variable into a disp statement. So again, this is a really nice review topic because it incorporates functions, data types, like numeric values and strings and arrays. So remember, to do that, you're going to still be grouping multiple things into one disp or title function, so you still are going to need those square brackets and the parentheses to indicate that it's a function that you're calling. But the difference is that you need to mix data types. So you need to convert all of your numeric values into strings. So that's why we use that num to string function, or num to str. But all that's really going on here is data conversion type, putting it all into an array, and then putting it all into a function. So it's really not necessary to memorize the syntax as it is to memorize or to understand what's going on. And then title would use the exact same. It would be the exact same syntax. X label, Y label, legends, they're all the same. They all need the same type. You guys have any questions about that? Okay. The next big topic is the topic of pre-allocating memory. Again, for example, on the midterm exam, there was a question that just asked you what's missing or what would speed up the code, and you can just memorize like, oh, I need to pre-allocate, and then you just put that there. But what I'm going to be looking for on the final exam is for you to explain and understand why you're pre-allocating and what is the purpose of pre-allocating. And there's a lot of ways that pre-allocation does not work that I see very frequently. So I'm going to show pre-allocation for a differencing function, because that way we can review differencing as well. So let's say that I just create some data that has some data that varies with x and f, which is just a sinusoidal function, and we just program a derivative. And remember, anytime you're using a for loop to fill in values of an array, like in a derivative, that's when you have to pre-allocate. So if you wanted to take the derivative at every x location in your data, then the first thing you do is you set up an array to store the values of your derivative, and you pre-allocate by like starting off each value with, usually we just use 0, but you can use anything as long as it just has a value, and it needs to be the same size as the array you're trying to take the derivative of. The big problems that you see here, and I'm actually going to write them out. There's a lot of different mistakes that happen. That does not say pre-allocation. These are the ones that I see most frequently. Okay, so the first one I see is this. Setting an array to an empty array doesn't do anything. It doesn't give it any place to put the variables. And I'll explain pre-allocation in a second, so you could, if you're still rusty on this, but this is the same as doing nothing. Another thing that's the same as doing nothing is just pre-allocating the variable as a scalar. Also does nothing. It does nothing that pre-allocation is supposed to do. Another really big mistake that I see, which is not doing nothing, it's just wrong, is I see a lot zeros length of x, which again creates an array. If the length is 10, it creates an array that's 10 by 10, and then you go in and fill in your derivatives, and you only fill in 10 of those, and then the rest are zeros because you didn't fill those in. So that is a very, very common mistake. So if you only put one input into the zeros function, it will create a square matrix with that size. And the last thing that I see very frequently, and this is the worst one because it usually causes an error of running out of memory, and that is that if you do 1 colon length of x, does anyone know what that does? Yeah, it makes this giant matrix. It makes a matrix of zeros that's 1 by 2 by 3 by 4 by 5 by 6 all the way up to length of x. So sometimes we were creating these arrays that were like 1,000 big. And so once you try to do that, there's not enough memory to store that array in MATLAB, so you get that error. So none of these work. These ones just don't pre-allocate. These ones are just, this one's just going to give you a bunch of extra zeros, and this one's probably going to cause an error. Okay, so what we do for derivatives then is once we pre-allocate, what that's going to do is it's going to create this array, df dx. I guess this is 11 big. So it creates its array, it has 11 zeros in it. So that way, when you start to go in and fill in your derivatives, so let's say that we want to use a central difference formula to fill in our derivatives, that means that we need to set up a loop. And inside the loop, we're just going to index everything using the central difference formula, which differences the points on either side of the point that you're trying to calculate the derivative on. And so when you do your like rise over run, your run is going to be 2 spacings wide because you're using the points on either side. And as you guys have now done quite a few times with derivatives, if you're using central derivatives, you're going to have to start your loop at 2, and you're going to have to end your loop at whatever the last element of your array is minus 1, because there's no points on either end of those endpoints to calculate derivatives. So what does this do? So let's just run through what this loop does. So it's going to start with I equals 2, and so it's going to fill in the second value of the df dx array, and all it's going to do is it's going to change this value of 0 to, I should have actually calculated what the value is, but I'm just going to make one up. So let's say the derivative was 2.5 or something. It's going to just replace that value of 0 with a 2.5. And then when it goes to I equals 3, it's going to replace this value with a 3. And it's going to do it one at a time. So I think most of you probably get the sense that that's what it's doing. If you don't pre-allocate, what it does, and that's why it's confusing, is if there's no array created first for it to replace values in, it's going to first go find in the memory of the computer, for the first derivative it calculates, it's going to find 2 spots because it needs to fill in the second element of array, so it needs an array that's too big. Then when it needs to fill in the third element of the array, it's going to ignore that array entirely, go find another spot in memory with 3 elements, and then it's going to fill that one in. And now it's already used up 2 and 3 spots in memory just to create the first 2 elements of the array. And as you can see, if you start building a really big array, that's going to be very slow because it's going to have to search for spots in memory for it to do that because it doesn't know how much it needs before it starts. So it's very slow, and it's a significant slowdown in the code. So the last little pieces of these derivative codes that are important are the endpoints. So there's a couple points I want to make here. If you're doing any endpoint derivatives, you just need to use one-sided differences. So you're just going to difference the best you can, which is if you're just using first order, you're just going to use the point next to the first point, so that'd be 0.2. And so you could go back and define this point. You could also do that before the for loop, it doesn't really matter. And then you need to do the end point as well. And I wanted to make a special mention about the end feature in MATLAB. So instead of using the length of x, which I find kind of clunky, it's really long and it requires a lot of parentheses, you can just use the word end, which I think a lot of you use and have seen. However, end only works if you've pre-allocated the array, right? If you didn't pre-allocate the array, you couldn't use end to access the last element of the array that you're trying to fill in. So there's kind of a lot to kind of think about with this whole code that I'm really looking for you to understand. And then, of course, since we're accessing an array that's already created, end is always usable because that array already has all of the elements in it. But if you're trying to fill in a number, like define a number, that's when you can't use it unless you've pre-allocated. Okay. Any questions about pre-allocation? Yeah.
So in the it says that you x, is that supposed to be multiplication or?
So this is how I write code myself because I like to write the operator before the variable instead of use parentheses. However, what I would say most of you probably do is you write this as divide by parentheses 2 times dx. Oh, sorry. Like that. That's not my preference because I find it confusing to know whether that dx is being multiplied or divided by. So when I learned to first program, I just always divided or multiplied each one individually. Any other questions? Yeah.
Could you explain just a little more why the size of x works for pre-allocation, but the length of x doesn't?
Yes, I can. So when you do size of x in MATLAB, the output is 1, 11. It's an array that has the dimensions of the array. When you do length of x, the output is just the number of elements in the 1D array, which would be 11. And so then if you put this into zeros, the zeros function would make an 11 by 11 rather than a 1 by 11. Any other questions?
Why did you start with 2 before this again?
Because if I started with 1 using a central difference, do you see how when I did I minus 1 here, it wouldn't have that value to access? So with central differencing, you have to skip the endpoints, and you have to define those endpoints derivatives with one-sided differences, either backward or forward. Okay. The next thing I wanted to cover, and this is probably my favorite thing to summarize, is sometimes when you're in a class, you're so focused on the details and all of the different labs that you're solving and all these different programs that you're solving that you never look back and think, okay, what algorithms did we write? And I summarize all the algorithms on that first couple pages of the MATLAB binder, and if you go look at this, you can clarify these things that I'm talking about. But there's really only 4. There's only 4 different algorithms that we wrote. We just applied them to different things. So what I like to do is summarize those so that you can compartmentalize all of these much simpler for yourself on the exam. So for example, the main one that we did about 1,000 different times is we did some variation of the find search algorithm. So some examples of finding and searching including anytime we were doing counting, binning, finding, etc. It happened in the linear interpolation section. We did a lot of different finding algorithms. When you wrote the binning algorithm in the planets lab, that's what it was. We did filtering algorithms, max algorithms. I already said interpolation, right? The max algorithm, etc. Oh, finding. Yeah, finding. So let me just show you. They're all the same. I'm just going to show you them all at one time in one code. So let's say that you have 2 arrays, and I'll just write one X array and one Y array. Now what I'm going to be telling you about we've done in multiple ways. We've done it using logical indexing, we've done it using intrinsic functions, and we've been doing it writing our own algorithm. So I'm definitely going to be asking you questions to connect all of those different things. So I'm just going to simplify the goal of the code by just saying find when a condition is true. And I'm just making up a condition. I want to find when x is less than 0 and y is equal to 1 element by element comparisons of those two arrays. So we've done a lot of those different things. They're usually applied to something, so it's just like a random number, but I think you can all imagine it. Okay, so I'm going to write it out for in a loop so you can see how you do it. So the basic idea for all of these algorithms is you set up a for loop that loops through each individual element of the array, and the arrays have to be the same size or you can't do something like this. So you can always base it off of any size or any one of the arrays, but the loop is just going to go through each one. So you have a big for loop that's going to go through each individual element, and then you're going to set up an if statement that does the condition check. And this is also pretty much always written the same. You write out the condition by putting in the condition x is less than 0, but indexing x with I so that it checks each one individually, and then using the proper logical and relational operator symbols to put in the full condition. And again, when you're doing, I won't be testing you on the difference between single and double logical operators, because we never did any problem where one or the other was necessary, or I just don't care, because it's just, when you're programming it, you just either take it out or put it back, and I think that's fine. Question? It's a double and, yes. I just was ignoring the fact that it didn't look anything like one. Okay, any other questions? Okay, so we did all these things. So the first thing that we did is a counter. So a counter is a form of this algorithm, just counts how many times the condition is true. So you start a counter off at 0, and then inside the loop and inside the condition, you just advance the counter. So binning algorithms do this, but there's more than one counter. And then we did counters a lot in while loops and other conditions as well. But a counter is a solid algorithm that we use throughout the semester. The next thing that we did in a lot of different quizzes and labs is that we saved which indexes satisfied the condition. So there's a couple different ways you can do it, but the way that I most frequently showed you, or was in the pre-labs, is that you initialize an array, usually I call it ind, to an empty array, and then inside the condition and the for loop, you simply take that array, add on the index, and replace the array with the new one. So if it finds 1, ind is going to equal 1. If it then finds 5, ind is going to equal 1, 5. And it just keeps tagging on the index for each condition that is satisfied. So again, this is for counting. This is for saving locations. And if you do just saving locations, then you can use that ind array for anything if you need to go back and access different variables to see when it was true. However, some of you, I noticed, instead of doing that and then using it to index later, you would create other empty arrays, like I'll create a second empty array called save, and then I'll just do the same thing. I'll take and add maybe the value of saved in the X array at that location. I'll save that. This is a little bit more hard-coded, so it's only going to have the value of the X that's true, not the index, but it is perfectly a perfectly acceptable way to do a lot of different algorithms. Another thing that we had to do in a lot of the codes where we're doing some sort of find or condition checking is that instead of saving the location or saving the value, we would just do a calculation. So for example, we would create a new array X, and you could pre-allocate Z. You could pre-allocate Z as we would. You might want to pre-allocate it with a different value depending on what the logic of the code is trying to accomplish, but basically if the condition is true, then a calculation is made. And if you remember back to one of the earlier quizzes when you were trying to add up like the cost, or everyone did something different, when a condition was true, this is one way to do this. Okay, and then the last option for this type of a code is mimicking how logical indexing works. So for example, you could create another array. I'm going to call it ind_logic, and I'm going to save it as zeros, the size of x. And instead of saving index locations like the find command does, what you can do instead is save initialize an array that's the same size with zeros, and then if the condition is true, you just replace that 0 with a 1. You can later convert it to a logical. Some operating systems and versions of MATLAB will just automatically use this as a logical if you use it to go back and access. That's the last option. So every one of the algorithms that we did something like this, you needed to do one of these things. So you can either write it out like this, which I required you to do on many occasions, or there's already intrinsic functions to do this. So for example, if you wanted to just find the locations, for example, you could just put this into the find command. It's one line, does the exact same thing. And with every one of your labs and every quiz where you did this, you could have done it either way, and people did do it this way. And then the other option is that you could use logical indexing, which is even easier because you don't need the word find. You can just put in a logical and relational condition, and that will automatically create that 1 and 0 array. And this is the moment when everyone feels sad a little bit, because they're like, why did we ever learn to write it with these loops, these if statements? And I assure you, there are reasons. And that's because you can't do everything using these simpler vectorized functions. You want to if you can, but once you start doing more complex systems in engineering, you aren't always going to be able to simplify them in this way. That is the first algorithm. I would say that summarizes a lot of what we did. Let me go over the next one. The good old sum. A sum algorithm is a classic intro to programming algorithm, and once you see it once, I feel like most people get it. But the way that a sum algorithm works, and we had to use it on several occasions, is that you have to initialize a variable to 0, and this will hold your sum. Then, whatever you're trying to sum, so let's say that we just want to sum x up from the previous example, you're just going to set up a loop that loops through all your x values. And this is very similar to a counter in that you're just going to take my sum and add on to itself, except for instead of adding 1 on to just count, you're going to add the value on so that you sum. So you're going to take my sum, have it equal itself, plus each individual value of x. There's no other way to write a sum algorithm. It's the only way to write one. And the only other alternative is using the intrinsic sum function, which you will be explicitly told whether or not you need to do that on the exam. Any questions about the sum or the find? Okay, the next one is writing difference formulas, or you could even generalize this type of algorithm into any repeat calculation. So if you need to write out a calculation element by element inside a loop, this is the only way to do it. So we did it mostly with differences. It came up in the linear algebra quite a bit. Did I write it? Yeah. Those are like the two main places, but you know, anytime you repeated a calculation, it's the same basic idea. Okay, so I already kind of wrote this out, so I'm just going to do it quickly. So you would just have some step size, you would do some pre-allocation, and I'm just going to do the derivative of x in this little example. And then a repeat is just going to create a loop that runs through all the values that you need to do the repeat calculation on. And then, based off of the mathematical formula that you're being asked to calculate this element by element calculation or repeat function, then it just patterns basically, like if you need to do I or I plus 1 or whatever it is. So if it's just a central difference, then you index using the central difference formula, which is I plus 1 minus I minus 1 divided by 2 divided by the step size. And I'm not going to do the boundaries on this because we just covered that one.
Would you say that the general difference or that central difference would be the main one?
No, not necessarily. I just like it because you have to account for both sides. That's why I did it. But no, I think actually everyone did a different one of those in the two different quizzes where you had to do differencing.
Would this be something like when we had to make the Christmas tree or the
Yes.
bacteria growth or something like that? Where
Yes, those are the other, yeah. So this would be the derivatives, linear algebra, and the population growth are all categorized as this. Or anything where you have to display or create an image or any of those. Anything else? Yeah.
So you're just saying next year's some arbitrary array.
Yeah, I'm referring all back to that same XY that I started with, but it doesn't, yeah.
What is that first one?
Here, or these. Derivatives, linear algebra, and population growth, yeah. And then let's talk about the last algorithm. So the last algorithm that we wrote a few different times is an error loop. So we did this in optimization. Gauss-Seidel. So that was the linear algebra algorithm that you guys wrote. And then the population growth. I think that's it. So an error loop is where you set up a while loop that runs until a condition is no longer met. And the one that we did in every single instance of the ones that I just listed is that you created some condition and you had a bunch of code, you updated that condition so that your loop ran until that condition made the loop condition false. And it was actually very similar in every instance. It was some error calculation, either as how something was changing from iteration to iteration. Actually, I think, is that what we did every time? Oh, but then actually that's not true. In the population growth, we did until they were all dead. So I guess that was a slightly different condition, but they're all the same basic concept, you know, of just having some condition in there. And I think for the sum, I didn't write down the different things that we use the sum for. Sorry, I was just going back because I think I didn't write any there. It's definitely the integrals, but I thought there was another one. I didn't do correlation this year. Didn't you have to do a sum one other time? Anyone remember? Oh yeah, labs. It was that lab where you had to do the max and min functions. I wrote it for you, so it's probably a little rusty, but that was the functions lab, whatever lab that was. The functions lab also, that barely looks like a word. Functions lab. That was the other one. Any questions about those 4 main algorithms? Isn't it amazing that that's all we did? Didn't feel that way, huh? Okay, now I want to move on to vectorizing, talking about vectorizing. This is where we're going to do several different problems. So I have the first one to even get you started, okay? So what I'm going to do is I'm going to either provide you with the vectorized or the loop form of a bunch of different codes, and I'm going to give you a few minutes to try to write the opposite one, and this will be on the exam. You'll be doing this exact same thing where I'll give you one or the other and you have to convert it to the other. And it's in the there's several of them in the practice test as well. And then I'll show the solution. And I think some people are always a little bit surprised because I talk about vectorizing code throughout the semester, but I never compartmentalize it like this. But that's because you've seen all of this, but now it's just you're going to put it in the right place now. So vectorizing, the book has a lot of vectorizing options, and if you Google in the MATLAB help, there's also a bunch of vectorizing examples there too. It also just shows up as not a word when you write vectorizing. Okay, first one, A. Which one should I do? I'm going to do the vectorized version. So I'm going to put all the loop versions on the left and the vectorized versions on the right. So I'm going to write the vectorized. And this is an easy one to get us started. It's just a vector definition. So here, what I'm doing is I'm writing out a function that depends on t, where t ranges from 0 to 1 with a step size of 0.1, and then I want the y value that corresponds to each of those t elements to be the sine of t. So this takes one calculation, one line, and it calculates all of the values of y at once. So what I'd like you to do is to do the same thing, but in a loop, element by element. So go ahead and get started on that. Jacqueline and I will walk around, and then I'll come back and show you. I'm only going to give you just a few minutes for this one because it's a pretty straightforward one. Okay, you've had a second to think about it. I'm going to show you 2 ways to do this. I wanted to review this because I've actually helped many people with these 2 ways, and especially because you guys work together a lot, I've noticed that you are confused about how they're the same thing. So the first way I'm going to show you is, I think, the most typical way. So you can create the T array the same way. Then you can pre-allocate the Y array with zeros that are the same size as T. Again, there's lots of instances where this is a required way to do a calculation, even though it's not in this case. Then you create a for loop that repeats this calculation of sine of t for every t value. So you're going to set up an index that goes from 1 to the length of t. And then you will just index y with your loop index. You will do the calculation, which is sine of t, but you must index t with your I index, and then that will fill in every value one at a time. Okay, so that's the first way. That's the way I think most people do it. The other way that I see people doing is they set up the for loop, but instead of creating an I index, they create an index that represents the t value. So the loop itself is running for t equal from starting at 0, step size of 0.01, and ending at 10. So now the index is the t value. So you want to define each element as just sine of t. But the tricky part when you do it this way is now you can't use your loop index as your array index because it's not an integer. Does everyone see that? So in this instance, you have to create a counter. So you'll have to initialize I as 0 and then count it. And I saw a lot of you doing this, especially in the optimization lab on that part 6, when you had to plug omega in for a bunch of different values. That would be how you'd have to do that. And you would want to pre-allocate y the same way as you did in option 1. So they both do the same thing, but they use their indexes differently. Okay, let's try a more difficult one. Okay, the second one I want to do is I'm going to do the loop form, and I'm going to have you do the vectorized form. That means you only have to write one line instead of lots. So this is going to be a sum formula, and the formula is just going to take an array of x's, square each value of the x array, add 5 on, and then sum every 5th one up. You know, just to make it interesting. And you can just assume that x is defined as just some array. Doesn't really matter what it is, but 1 to 10,000. So you already know what x is. Does everyone get the task and the math syntax here? So you're going to take each element of x, square it, add 5, sum it, but only sum every 5th. Okay, so let's write that out. So in order to do this algorithm, you need to have a x array. And what I'm going to do is I'm going to create an array that holds the calculation of x squared plus 5 for each of the elements that are going to be summed. So I'm going to create my sum ind and pre-allocate it with zeros. But I don't need to have one of these at every element of x. I only need it at these elements of x. So I'm just going to do the same thing, 5:5 length of x. Now this part is a little bit tricky and it would take you a little bit to think about how to index it, but don't worry too much about this because I want you to do the vectorized form of this, not the loop form of this. But if you were going to do this in loop form, you would need to first do this calculation. So what I'm going to do is I'm going to create a loop index that starts at 5, goes every 5, and ends at the last element. I'm going to calculate what's in parentheses at each one of these I locations. And then I've already pre-allocated my sum end here. And I'll fill in this index in a second. But for now, I'm just going to fill in what goes in the parentheses, which is x of I squared plus 5. So that's just straightforward because we've already pulled out the right elements through our loop index. So that right-hand side is straightforward. But the tricky part is now our index is off. So you could either do the counter that I just showed you in the last one with option number 2, or you could just do I over 5 because it's an even jump, and that will make sure to index that variable correctly. So that will get us all the things we need to sum, and then all we need to do is sum them because we already did this part of the calculation. So this is just going to be a sum algorithm that we've already done. You could have done this all in the same loop, but I thought that would be confusing, so I just put it into 2 separate loops. So I'm going to create an array called mySum. I'm going to initialize it to 0. Then I'm just going to loop through all the elements of mySum end that I created up there. And then I'm just going to write the sum. So it's just going to be mySum equals itself plus each element of that calculation we did above. And again, I'm reusing I, which is fine. You can do that with loops that go down. It'll just, now I will have this this loop index. And again, I could have done both of these at the same time and had the sum and the calculation in the same loop, and it would have condensed it a little bit more. Okay, so what I'd like you all to do is spend about, I'm going to give you about 5 minutes to think about this one, of how to write the same thing in one line using vectorized notation. So keep in mind that when I ask you to write anything in vectorized notation, that means that you can use any intrinsic function, because intrinsic functions in MATLAB are always vectorized. Okay?
Would in order to it's only taking that song essentially so it's taking actual so like
Okay, it looks like a lot of you have got there. So let me just write out. I don't think there's that many ways to do this one. So someone did it a different way, like a significantly different way, you should let me know. But we're just going to define my sum just the way I did it in the other code. So what you're going to do is, I didn't really leave enough room, but you're going to first start by calling on your X array and accessing only the elements of X that are needed in the sum, so from 5 to end with a step size of 5. And then, someone just say something?
So we're already given X, so.
Yes, we're already given the F.
You could write it as X equals 5, 1, 5, 1.
Or you could do that.
Okay.
Yes. So you either need to create an X that does that, or practically this should be able to do it to any X, so this would be kind of a better answer. But then you're going to do the vector algebra to do this all at one time. So you're going to dot square each element of X, add on 5 to each element of X, and then sum. And that does the whole thing. Any questions about that? Do you love that? Yeah. Okay, let's do one where we do a find, because I think that's a really good one to vectorize. So, given an array D, so you're given an array D that has some values in it. The task is to find the values in the array that are less than 5 or greater than 9. Made the mistake so many times of saying that are less than 5 and greater than 9 because I wanted all of them. But logically you should say the word or. So if either is true, you want to save them. And we want to save the values to a new array D COND for like D that fit the condition. Okay, so for this one, I will show you, I'm going to show you the loop again, and I'm going to have you vectorize it, okay? So the loop version of this I've actually already shown you. You just do, when I showed you that first type of algorithm that we wrote. So in this case, you don't know how many elements satisfy the condition, otherwise you wouldn't be writing the script, right? So you have to save the array as an empty array that will then get filled in, and then it's just your classic find loop that loops through each element of D, and it checks a condition that'll all be indexed. So you're going to check if D is less than 5 or if D is greater than 9. And you'll index D with the loop index. And then, in this case, since I asked for the values, you could either save the indices and then plug them back into D, or you could just start off by just saving the values from the beginning, and that's what I'm going to do. So you just set up D condition equal itself, but add on each D of I that satisfied the relational above. So that is your loop version. So I would like you to spend a few minutes vectorizing, doing the vectorized version. For this one, there are quite a few ways you can do it, but you can do it in one line. And this assumes that you already have D defined. Okay, I think most of you have got this one. So let me show you the best way to do this one. Or not the best, but this is I think it's the only way you can do it in one line. No, it's actually not. So the way I would do it is I would first create the logical and relational condition. So remember, when I do this, it'll give me ones and zeros. Ones where that condition is true and zeros where it's false for each element of the array. And then you can just plug that directly back into D, and that will give you your values. You could do also D of find of that. That will do the same thing. Or you could create two steps, one where you save the indices or the logicals and then plug them back in the next line. All of them are fine.
Why would that equal the D of 5 of that? How does that?
So this is just going to give ones and zeros. Find is just going to give locations, and arrays can be accessed using either logicals or locations. Mhm.
So if I did like find d of 1 through length of d is less than 5, and then the same thing for the 9, what would that do?
It would do the same, but you don't need to access arrays if you're accessing all the elements of the arrays. It's just unnecessary.
Okay.
You know what I mean? You
Would I
only,
be marked off for that?
not if that was the question. If it was asking you to vectorize, because it still is vectorized.
Can we really quickly go over which one would be better? Like, isn't one required less?
Not really.
Power than the other.
Find and logicals, there's not one that's better.
And this is kind of exactly what you're going to do. This is like a loop or a vector, and then say either find a loop
Yes.
or find a vector.
Definitely, yeah. Okay, let's do another one. Oh, by the way, sometimes on those last algorithms that I give you, sometimes I specifically say you can't use intrinsic functions, and sometimes I don't. So pay attention to that, because, for example, on the midterm, one of those could be written in one line, I think, because I didn't say that. I don't remember if it was this class or another class, but it has been. And if you understand vectorized code like this, it makes it a lot easier to write the code. So make sure you pay attention to that. I will be very specific of whether or not codes can include some of these intrinsic functions. So I'm going to create an array X, and this is the array that I want you to write the algorithm that counts the 7s. And again, I feel like for this one, since I've already done a counting algorithm, I'm going to show you the loop version, and you can vectorize it. So a counter just initializes a variable. We typically use CT, and then it loops through all of the elements of the array that you're counting, and it places a condition to check. So in this case, you're checking equality, and you index the vector with the loop index so that it does it one at a time. And then every time that's true, you're going to take count, add 1, and replace the value of count with the new one. So the goal now is to vectorize this. There are actually there are lots of options. So go ahead and spend a few minutes thinking about how to write this equivalently in one line. All right, you guys are doing good. You got it? No, you technically use the logical function. That's what I'm saying, it actually depends. Some versions and some others. So I wouldn't really focus on it. Like some version of it had used the logical word and convert it, but not that. Okay, here are some of the solutions. I actually didn't use some in my solution, but yes, that is a pun. But first one, this is how I did it. I did x equals 7, and then I did the find command to locate the locations where that was true, and then, shoot, I ran out of room. And then I did the length of it. That's what I did. I wouldn't say that that's the best way, but that is honestly how I did it. I would say that probably the best way, and this didn't used to work because you didn't used to be able to sum logicals, but now you can. So now you can just do the sum of the logicals. So x equals 7 will give you ones where it's true, and then the sum will sum the ones. Even though they're logicals, it still sums them. And so that's another option. Do you want to do anything else? Or it would, because what it would do is find would give you 4, 5, 7, and then it would sum those numbers, which wouldn't be counting them. So you can't mix these two. You can only use length with find and sum with the logicals.
How would you say the actually do the same thing?
Then you would just do find.
Okay.
Yep. Any other questions on this one? Isn't it just like weird that you can do it so simply? It's like, that's what I think most people, and the thing that's weird is some people have been doing this all semester, and some people have always stuck with loops. Like everyone does these things differently, so I just like to kind of combine it all in one. The last thing I want to do today is I want to pass out a condensed code task. It's actually either exactly or very similar to the one we did in the pre-lab when I first introduced loops, and there's another one on the practice test. There will definitely be a condensed code on the exam, and the idea is that I'm going to give you a very long code that will probably take the whole page on the exam, otherwise it doesn't make sense to use it. And then you just need to find the pattern and rewrite it in a shorter amount of lines. People find this a little bit stressful that their codes aren't that much shorter. That's okay. You're just trying to write it as short as possible.
How are we creating that?
I always grade those questions and I just roll the dice. No, I'm just kidding. No, I always grade them. Very cool. Everyone get one? So for this code, the idea is to generalize everything. So I noticed when I look at pre-lab, when you guys do this for the pre-lab, some people, for example, never generalize the color of the line or the title of the line. So the best solution to this is to generalize everything. You can do it with functions, you can do it without functions. I think the easiest way to do this one is to just put all the code in a loop and index everything that repeats. Okay, so I'll give you just 5 minutes to kind of work on it, and then I'll show you my solution. And that will be the last little exercise for today. Jacqueline and I will stick around after this to answer any additional questions you have. Okay, it looks like most of you are getting there, so let me go through it. I just wanted to show you how you can approach these types of problems too, because for some people they find them a little bit overwhelming. So what I like to do is look first at the problem and try to indicate all things that repeat. So for example, and try to find patterns. So first you can see that in the definitions of the y's, you'll notice that the coefficient that's inside the sign is what's changing, but everything else is the same. So that's what repeats, or is the same calculation repeated with a different value. Another thing you'll notice is the subplot index, or third input, also does the same thing. You'll notice that the color of the line changes for each one. The title changes. So you'll see this one has a 1x, this is a 2x, etc. Anything else that I missed? Yeah, the title. Anything else? So those are the things that you want to be able to write one time, but have them be general in terms of a loop index. So what you can do is first start off by defining an x, because the x doesn't change, it's always the same. So you'll do that outside of the loop. Then you're going to create a loop, and you already saw that the pattern is that everything is either 1, 2, 3, 4, 5, or 6. So you're going to create a loop that runs for all 6. And then you're just going to start condensing each of these lines into one line. So the first thing you want to do is define your y. And I saw this was the thing that I saw people doing a couple different ways, so don't overcomplicate it. So x is an array and y is an array, and all you need to do with those two things is plot them. So as long as you define them and plot them, you don't need to have them for anything else. So for example, you can just do a vector definition of y based off of the sign, and then change the coefficient with the loop index. And then what I'm doing is every time the loop runs, I'm going to overwrite y, because every time y is going to be the same size, it's just going to be a different y. I saw some of you indexing y with I, and while you can do that, since there's no need to save those values, you don't really need to save them. But if you want to, the only way to do it is to put y of I comma colon. And that way, each of the 6 y's will be on each of the 6 rows of y. And of course, you should pre-allocate y somewhere so that in whichever way that you decide to do it, it has the right size. But I'm just going to overwrite it. Then I need to next create my subplot command. The nice thing about subplots is if you're using subplots, the first 2 inputs should always be the same every time you call it, right? It divides the figure into 3 rows and 2 columns. And then it's only the 3rd input that changes each time you call it to indicate which one you want to plot into. So I'm going to put my I index into the subplot command. Then you're going to call out your plot function. And now, because I'm only using x and y as my variables, and I'm just overwriting x for each time the loop runs, I'm just going to put x comma y. Each of the plots has a different color, so I wanted to show you 2 different ways you could do that. The first way is to use cell arrays, which is what we've done mostly in this class, because cell arrays make it so that you're saving an entire word, not a character. So it doesn't really matter for this case because our words are all the same number of characters, so you wouldn't necessarily need to use a cell array. But I'm just going to create an array that has the proper order of the colors in it, like this. And by the way, I do this all the time when I'm writing plotting algorithms because I hate copy and pasting plotting algorithms. So I always write my plotting algorithms either in function or loop so I can just reuse them. So you can also do this with color maps as well to create color maps that range from whatever value you want it to. Then when you want to use that shorthand color code, you'll just call color, that array, but you've created it as a cell array. So remember that cell arrays have their own data type, and so if you just do color parentheses I, then that's going to be a cell type, which is not readable by the plot command. So you need to use curly brackets, and what curly brackets does is it converts the cell into the original data type that was saved in that location of the cell. So since the location was originally saved as a string in its definition, when you access with the curly brackets, it puts it back as a string. So if you don't put the curly brackets, the plot command is going to throw an error. And then there's no change in the line width. It's always 2, which by the way, pretty much always have to increase our line width to 2 when it's 1. It's not dark enough to see in most prints. And then the X and Y label are the same, so we can keep those the same. And you do need to put this in the loop because you need to label the X and Y axis in every subplot. And then the last thing is the title, and I already reviewed this for you when I talked about the display and the title functions, but this is an instance where you need to incorporate both an array to put in multiple strings and a num to string to convert your loop index into a string. So to do that, you're going to start off with sign, parentheses, then you're going to end the string, and then the next character is going to be whatever the number, so you're going to do num to str of I, and then you're going to concatenate on the last parentheses, end the array, and the title function.
So the num2 string doesn't need the whatever. Quote.
No, because it takes the number and converts it into a string. It's just like if you have like m equals Shannon, you don't need the m to be in a string because it's already a string.
So you need X in your second. X.
Yes. Thank you. Yeah, so it'll need to be x parentheses on the last part of the string. Anything else that I forgot? So let me just show you the other way you can do the color in case you're interested. So because this is just a string, I find people find string arrays confusing, but they're actually kind of straightforward. If you just put strings in a regular array, I could just put K, R, B, G, M, C. And I could just put them all in the same array. I don't even need to separate them with commas because it's gonna put them all together anyway. And then here I could just put color of I. That would also work. That only works because the code that you're using for the plot command is one character. So it's kind of a special case where that would work. Yeah.
Do you need single quotes around that color line?
No, because this is a string. You actually don't even need the square brackets around a string. If you create a string, like if you just type color equals the string, and then you do color of 1, it will just give you K. So that's the default way that strings are. That's why we use cell arrays, because otherwise if you were trying to put a bunch of names together and you wanted like Shannon, John, and Sally, you'd have to like call out the first 6 elements to get Shannon and then the next 4 elements to get John, and it's actually really complicated. And before they had cell arrays, that's what you used to have to do with strings in MATLAB, but now they have this new data type. I don't know, it's been around for not very long. Yeah.
The second way you did the color of I have to be in a string?
No,
Or is it already?
because it's in a string here. And you don't even need the square brackets either. That's optional. Is there any other questions? Yeah?
Could you do the title as a string as well, do like X or
You could do that.
Or give your title just a T and then curly brackets I.
Yep, you could do that. That isn't, that is going to be a little bit more clunky than this, I would say. If you can do it this way, this would be better because you're creating another array. But I don't think there's any other way to do the color bar except for to do it this way, if that makes sense. Any other questions? Okay, yeah?
Why don't you have to help the count of I
Because I'm using a for loop, so I always has the counter value. So Jacqueline and I will stick around until everyone's gone. So if you have additional questions for us, questions on the practice test, feel free to stay around and ask.